Good morning, everyone. Welcome to the ML in GW Astronomy workshop. First, I would like to invite Professor Sriram Kumar to say a few words about our department and about the Center of Strings, Gravitation and Cosmology.
Thank you. Welcome to Chennai. On behalf of the Center for Strings, Gravitation and Cosmology, let me also welcome you to IIT Madras. One of the mandates, primary mandates of the center is to increase or enhance the level of academic activity, and I'm glad to see two strongly interacting binaries, namely Prayush and Chandra, are emitting gravitational waves to be detected by AI/ML tools. I was requested to say a few words about the center as well as the department. The center presently consists of about 7 faculty, they are involved with the center, about 6 to 7 postdocs and about 10 odd graduate students, and many undergraduate and master students regularly interact with us. And as I mentioned, one of the primary goals is to increase the level of activity. I see that many of you are participating here physically and some of you virtually, and we would strongly encourage you to visit the center. Chandra, please kindly get in touch with Chandra. We should be able to support your travel as well as stay. The center is part of the department, and the department itself consists of about 57, 58 faculty, and there are people working on a wide range of areas. I will not be able to, ranging from experimental condensed matter physics or various aspects of condensed matter physics to cosmology. I will not be able to do justice by listing the various topics. And there are many young faculty working on variety of aspects, including many who are using AI/ML tools not only in gravitational wave astronomy, in other areas of research as well. With those remarks, let me wish you an enjoyable and productive meeting. And I'm sure Chandra has attended to all your requests, and if there is any help you need, you are welcome to reach out to Chandra or any of us. Thank you very much, and let me wish you again a good meeting.
Thank you, sir. I would now like to invite Professor Shashwat Kapadia to chair the session.
Who is going to speak is Professor Anand Sengupta, and he is going to talk to us about accelerated CBC inference with Meshfree surrogates and SVD-based model reduction.
First, thank Chandra and the other organizers for Prayush and other organizers for giving me this opportunity to talk about some work related to accelerated CBC inference. This is particularly of interest because we are entering the era of the next generation of gravitational wave detectors. People are also talking about space-based gravitational wave detectors. So gradually the whole spectrum of gravitational wave detection is going to shift down lower by an order of magnitude, hopefully in the next 10 years. And you will find that what I am going to argue here is that it's going to get progressively harder to reconstruct the sources. So you will detect a gravitational wave, but then the next interesting thing for you to do is to figure out what are the masses, how fast are they spinning, where in the sky are they, and so on and so forth. A lot of astronomy is basically based on this inference. And what I'm going to talk about through the next few slides are basically it's kind of a breadth view of some of the efforts that people have made over the years and where we stand at present. Of course, this is not an exhaustive kind of a review of all the methods that people have developed, but some of the interesting ones that I find which are quite clever. So this is with ETA of 2030. Now, to this, not only are we going to have an expanded network, which have obvious science advantages, but we are also going to have better detectors as far as seismic isolation is concerned. And so therefore, the overall bandwidth of these detectors is going to shift towards lower frequencies. So hopefully, and then of course we will over the next few years we can also expect upgrades of these detectors, so that we enter the era of the third generation detectors, where the lower cutoff frequency is going to be a few hertz, hopefully. So this is the scene, and I want you to keep this in mind. So this is this is nowhere related to what I'm going to talk about, but I just wanted to tell you that this network is very important, because for instance here I have the source localization of a binary neutron star source, and this green circle here is a 90% credible interval of the area localized by just the LIGO Livingston and Hanford detectors. If you add a Virgo detector, which by no means is actually detecting it, so if the Virgo detector, the trigger for this particular source is actually sub threshold, it's at about 5 point few, but that immediately helps you to localize the source. But if you had a LIGO India detector at a similar sensitivity as the Virgo detector, but located in India, you can see that that further reduces this localization to sub 10 square degrees. So if you could the message that I want to give is LIGO India detector could play a very vital role even at very early stage of commissioning, and therefore we have to prepare all the tools that we have at our disposal to basically be able to reconstruct these sources as quickly as possible. Okay. So this is another message that I wanted to give. Very quick PE primer, and I'm sure you will hear more from other speakers. So you have a gravitational wave data, which is essentially some astrophysical signal buried in noise, and basic statistical properties of this noise are known. That is, n is a realization of a Gaussian noise with zero mean and unit variance, and it's described by a power spectral density. And the other thing that we assume is that a forward generative model for this waveform is available. So we now have a zoo of waveform models. We have waveform models that are purely theoretical. We have waveform models that are numerical relativity inspired, and so all sorts of waveform models with various degrees of physics plugged in are now available. So we do have a forward generative model for H. Right. So now what we are really interested in are putting an estimate of these parameters lambda which describe this waveform, and that is to our rescue we can use the stochastic inversion using the Bayes theorem, which is given up to an overall normalization constant as the product of the likelihood and the prior. And the good news is that if such for such probability distributions, one can always sample this distribution. So if you know a probability distribution up to an overall normalization constant, you can use a variety of to actually sample these. So for instance, the ones that we use now are Markov chain Monte Carlo, for instance, or nested sampling techniques. So if I know the right hand side up to an overall normalization constant, I can give you a bunch of samples which, if you take a histogram of it, will start looking like the desired posterior distribution. So that greatly reduces the computational burden on this. So this likelihood function can be calculated assuming Gaussian noise at every point in lambda. So if you have a point in lambda, you can basically calculate this right hand side, which consists of two pieces. One is called the overlap integral, and the other is the norm of this template H, which is calculated at a point in the parameter space lambda. Now it turns out that the bottleneck for the parameter estimation calculations turns out to be this overlap integral. So there are basically two pieces. One is to actually physically having to generate this waveform H, and then calculating this integral. So as you go to next generation detectors or space based detectors, you will turn out that been pressing all so As you go to the lower and lower in your sensitivity in frequency, it will turn out that these integrals are become harder and harder to calculate. So a bunch of new techniques, or well, not new anymore, but a bunch of innovations have come in, and I would like to just point out a few. So for instance, these are some of the names that you might have come across earlier. So quadrature summation, for instance, relative binning, interpolation with Chebyshev polynomials, multi-band methods, and Meshfree methods. So this is the method that was developed by my group, but and I'll come to it at the very end. But I want to spend a little bit of time just talking about some of the the core idea behind some of these techniques, which helps to accelerate the parameter estimation process. I also want to point out, and this is something that I mentioned earlier, that as you go from 04, which is part of that has already happened, to 05, these are the science runs, observation runs, you expect to operate at lower and lower frequencies. So for instance, between 01, which is this orange curve here, to 04, which is this gray area, you see that this has clearly pushed the lower cutoff, the seismic cutoff frequency, to lower and lower frequencies. So the signal duration scales with this as a very steep power law. So for instance, if you want to go from 04 to 05, you end up with 6.5 times longer signals. So that increases naively if you kind of calculate. This increases the overall computational time by the same factor. But if you kind of push it to say decihertz detectors, it this factor can be as large as 200,000, for instance. So the amount of computational cost that you have for your current analysis is going to get multiplied by 200,000, which is ridiculous, of course. But so we do need some novelty, or some new features or new techniques to get around these problems. So here is the same thing, basically, just to give you a visual representation. So if I try to understand this bottleneck that I was talking about, this overlap integral scales linearly with the number of samples. So this is the overlap integral that appears in the likelihood, and if there are ns samples in the waveform, then it takes order ns to evaluate this expression. And as I said, if you go from 04 to 05, this is going to take 6.5 times longer, which already means that whatever you could do in a few hours to a day would probably take you a day to a week. But then it will be practically impossible to carry on the same scaling to decihertz detector, where you go all the way up to 0.1 hertz seismic cutoff, or not seismic, but yeah, the lower cutoff frequency of that band. And fast P is important for electromagnetic follow-ups. I am not going to spend too much time, but I just want to point out one little thing, that in order to do follow up these mergers of binary neutron stars or neutron star black hole mergers, we need to basically figure out the what it ends up with, for instance, and the final mass makes a big deal about what the final product is going to be, whether it's going to be a hypermassive neutron star or a prompt collapse to a black hole, or something like that. So, and we are entering an era where we'll have very limited observational resources for a large number of detections. So we are going to be sensitive to a larger and larger volume in the cosmos. So basically we are going to enter an era where we have to divide limited observational resources for large number of detections. So therefore this is another reason why this kind of techniques need to be developed. Now I am going to go through a few of these techniques. For instance, the first one that we are going to talk about is this empirical interpolation. We will come to that in a minute, but I just want to show that through a toy example, that we can imagine that h of x is your toy gravitational wave signal, and this has this kind of a functional form where x could be frequency, for instance. And what we want to do is have an empirical interpolant of this form where we kind of approximate this h of x through these basis, this empirical basis functions. So b1, b2 and b3 can be found, and you can see that this h has to be evaluated at only 3 of these interpolating points, f1, f2 and f3. Purposefully I have taken hx to be a cubic function, and b1, b2 and b3 to be a quadratic basis. So you can easily appreciate that you can have a low order representation of something that is oscillating very fast. And the idea is that this interpolant should match h of x exactly at the nodes, but in between that they can differ. So we can choose interpolation nodes very carefully at these 3 points. Suppose this domain is 0 to 1, and requiring this condition which guarantees that this approximating function actually has the same value at f1 as that as the true one. So that is given by this condition. Bi at fj is basically this Kronecker delta delta ij, and you can use that to basically find these 3 quadratic basis functions, and in the quadratic basis you can write this approximate form of this wave function as the sum of these 3. Now here I have plotted the true function h true and this approximated function, and you can see that, well, in this particular limiting toy model, yeah.
How are these B's related to the usual Lagrange polynomial?
They are actually, I mean, so they can be constructed out of the Lagrange polynomials through this this condition.
So the nodes are not necessarily roots of any orthogonal polynomial?
Well, nodes can be found through a greedy algorithm, but they can also come from what you are suggesting in a standard Lagrange interpolation. That is how they come. But in this case, well, you can these are not random. They are carefully chosen to be the. So you can see that f1. So this is a quadratic basis, right? So one of them is a constant. The second one is a linear piece, and the third one has curvature. So you pick those pieces where you get the maximum information from these 3 pieces, and that's how these nodes are constructed. But they can also be constructed in a very systematic fashion.
So if, for example, you took higher order interpolation, then the
it will be exact in that
nodes
case.
will cluster towards the boundary?
Yeah. As it happens for Lagrange interpolation, it clusters toward the boundary, and you see that in a formal analysis in the the paper which I am going to refer to. If you try to find the nodes through a greedy algorithm, you find that the nodes are clustered towards the boundary. This is a toy model just to explicitly show that such kind of an interpolation through a empirically obtained basis is possible, and I will show why this is important. So we can do the same thing for gravitational waves, for instance. So where the gravitational waveform h of f in the frequency domain with some parameter lambda can be written out in terms of these bases, which are purely functions of frequency, but then these are coefficients which are nothing but the same gravitational waveform that are calculated at a few nodes basically. Now why is it useful? I mean, why are we trying to do all that? Because now if you try to take the inner product, this infamous overlap integral, you can see that these are now just coefficients. So you can basically transfer the inner product with d onto these basis functions, as you can see over here. So this inner product can be now written as sum over the inner product between d and bi's, but remember that bi's have nothing to do with lambda. So when you are sampling this the posterior distribution, you can calculate the data related part can be calculated pre-computed only once, and you can assign this as some weight Wi, and this reduced order quadrature basis, this inner product is written just as a weighted sum of the evaluation of this waveform at only a few points. Earlier we were summing it up to, I mean there were L multiplications, but now this Wi can be pre-computed, and this is just only capital N multiplications instead of L. So typically L is a few hundred thousands, and N here is a few hundreds. So you can easily see that you can get speed ups of factors of 30 to 150 as described in this paper by Canizares et al. These can be obtained just by this little trick. So all you have to do is basically try to express these waveforms in some suitable empirically obtained basis. So this is one trick that people have used. So the idea is that, well, you have the posterior known up to an overall normalization constant. So you plug it into some sampler which keeps on proposing new points based on the likelihood. So you have to calculate this over and over and over again. So what you do is you pre-compute this data related weight once before you go into the sampler, and then for every new point that the sampler proposes, you basically carry out these n multiplications. N is much smaller than L, and that's how you win. So this likelihood calculation becomes much faster. The second clever technique that I would like to point out is by these authors. Now basic idea is sample the waveform sparsely for portions where the full frequency resolution is not required. So for instance, if you have a waveform that traverses from say a very low frequency to a very high frequency, it's going to spend a very long time at low frequencies. So why would you sample it at the full Nyquist rate when it is going through say low frequencies for a very long time? That's the whole idea. So these guys show that for binary neutron star system, implementing this idea could give you an overall gain of a few hundred. Basically the idea is not to oversample the overlap integral and these posterior plots essentially show that the standard and the multiband interpolar. Why multiband? Because you divide the entire frequency band into little pieces, and in each piece you change your the sampling rate, and basically that reduces the overall number of points over which you need to carry out the overlap integral, and that's how you win. So this is the second method. The third method that I would like to point out is one that is very popular and probably one of the smartest methods that we have right now. It's a method by Zake, Venumadhav and others. So the idea is that when we are trying to do a posterior sampling of the posterior distribution, we are not going very far away from the most likely point or most likely parameters of the binary. So basically the difference between some reference template H0 and a nearby template is a smooth function of f. So basically R of f tells you that so what you do is you divide this bandwidth into a large number of bins, and in each small bin of frequency there is a very small deviation from this reference waveform and the waveform that you are really interested in. And so what you do is you calculate all the inner products and so on, overlap integrals with this reference waveform itself, and then for any new point you just figure out these R0 and R1 coefficients and adjust these two integrals. So A0 is pre-computed against the reference template, and A1 is the next order in this expansion, and that's what you do. So basically you have to calculate this A0 and A1 only once, and for any other template you just keep on supplying the coefficients little r0 and 1, and that is how you basically end up a much faster way of evaluating this. This plot here shows you the log likelihood from some reference L0 for different bins. So, if you have fewer bins you expect a larger variation, but if you increase to a larger number of bins then the difference is much smaller. Finstad and Brown applied this relative binning technique to a coherent network of LIGO-Virgo detectors, and you can see that with and without the relative binning applied, the posterior distributions are nearly identical. I am going to skip this, and how long do I have? 5 minutes. Okay, all right. So, finally, I would like to talk a little bit about how to interpolate the likelihood using Meshfree techniques for using radial basis functions. By the way, a network of radial basis functions can be equated to a one layer neural network essentially. So, I do not think I will have the time to talk about that, but let me just give you the basic idea behind it. So, suppose you have a function s of x, you can essentially expand it in a radial basis. So, phi is a radial basis. In this case we have taken this to be Gaussian functions. So, they are radial and very symmetric. Xi's are the nodes. So, in this case there is one at x1 and 2 and 3. So, there are these 3 nodes at which the Gaussian functions. So, for instance, the one centered at 1 is this blue one. Sorry, the blue one is the actual function, is this green dot dashed line. The other one is this red one, and the third one is this dashed blue cyan colored one. So, any function in this domain can be written as a linear combination of these radial basis functions. And so, but then how do you figure out these coefficients lambda I? So, lambda I are found by by solving this constraint equation, that the interpolating condition demands that at the nodes the function is known. So, once you have that, then you can solve these constraint equations to find them. So, the idea, I mean, if you look at the log likelihood function, which is this is the phase marginalized version of this, looks so the right hand side again consists of two pieces. One is this inner product between the data and the template, and the other one is the template norm. Both of them can be, so this inner product can be written as a vector, because you need to slide the template against the data to get a vector of values, and this norm is a scalar. Now, both of them can be interpolated using singular value, radial basis functions. And why do we have that confidence in it? Because, so for instance, if you look at the time series, you can expand it in a singular value decomposition, SVD basis, and these coefficients are very smooth functions on these parameters. You can clearly see this. So, the idea is that these coefficients can be written out in this RBF basis, and there is, if you figure out these coefficients R alpha and Bj's, then you basically do not have to, there are two advantages. You do not actually have to physically calculate the overlap integral, and you do not really have to calculate the waveform at any given point that the sampler throws at you. So, I am just going to stop by showing you a recent result where, so for instance, here is an example from the GW 170817, where we reconstruct this using the radial basis functions. And the speed ups can be quite phenomenal. For instance, if instead of 2 to 3 hours, you can basically reconstruct this in a few minutes. Of course, this depends on the number of live points and various sampler settings and all, but these are just representative of the kind of advantages that you can do. I would like to end by saying that we have tried to extend it to space-based detectors, and one of the difficulties over there is that this method works when you can cleanly separate the intrinsic and extrinsic parameters. So turns out that for space-based detectors the signal lasts very long in duration. So as a result of which the antenna patterns become functions of frequency. So it is, a clean separation like that is not possible, but you can still do, some tricks can be used over there, and we have managed to do it for LISA, but I think a lot of new innovations are required to make it even better. So I think I am going to stop over there. I will take any question that you have. Thank you.
Maybe time for
Generation of ground-based detectors.
Yeah.
For example, if the SNR is quite high, does it show some bias or something?
No, it doesn't show a bias. So for instance, for 3G detectors, the lower cutoff frequency is going to be 5 Hertz. So again, you are going to see the source for hours, even days, right? So because over a few hours the earth would have rotated, so your antenna pattern is going to change, but it's going to change very slowly. So you can use, say, stationary phase approximation to kind of decouple, basically calculate the antenna pattern only at the stationary point and still be able to do this. So this is something that
So I'm just talking about like the late-in spiral part.
yeah.
With respect to BNS thing, so even if you just increase the cutoff frequency to be say 20 Hertz or so, and then do the P, and then see if there are some biases in estimating, for example, tidal deformability and those type of things. When the SNR in the late-in spiral is quite high,
Right.
that means the tidal deformability constraints are quite narrow. So is there any bias?
So bias coming from where? From this technique itself or in general?
No, from technique itself, not
I don't expect any, because you are, there is nothing that is happening here that would introduce a bias unless, the waveform model itself has, something in it. I haven't actually done it myself for high, we have done it for very high SNRs, and, we don't see any such thing.
Yeah, if it is not showing up for like lower one,
The only problem that I see for 3G detectors is not to take into account the rotation of the earth. So that is the only thing that I see.
okay, go for it.
So you have shown the result for the 79 seconds. The SNR of the 79 seconds was quite high.
Yeah.
How does this technique perform for that?
Yeah, good point. So if you go to the absolute threshold, it's likely that this will not work very well, because you need the fact that you can project it onto a RBF basis relies on the fact that there is something to pin your RBF basis functions, right? So I don't think that threshold study has been done, but we have results from, say, SNR 10 onwards, and we seem to be doing reasonably all right, but it's interesting to go below and see what happens to, yeah.
So I had a couple of questions. One was, so you showed a whole list of methods.
Yeah.
I was wondering how many of them are, so to say, orthogonal, in the sense that can you apply several of them to for drastically improve the time, and whether such a study has been done or not?
No, not to my knowledge. For instance, Chebyshev interpolation is again a grid based interpolation. So I think that died its natural death, because if you go for, say, higher number of parameters, it scales, the number of grid point scales very quickly, it grows very large. So that cannot be used. I think some groups are trying quadrature summation. I am not sure whether how the status of these, but my point of showing these was to show the innovations that have gone into speeding up this calculations.
My point was that whether, say, for example, you can combine relative binning with Meshfree method so that you have the power of both, or are they they are not completely orthogonal. It's like,
This is something that we are thinking about.
oh, you're thinking about
Yeah.
Okay.
But I mean, we don't have anything to to show you yet.
Right.
Yeah.
And my second point was that you mentioned the need for rapid parameter estimation, and it seems like most of these methods tend to cut some corners on precision, if I can put it
Yeah, of
roughly.
course. Yeah.
So do you worry that when one does things like this, that one may miss out on, say, subtle violations of GR or subtle kind of environmental effects, or do you think that that is not a worry?
I think right now all the effects are basically there are many other effects. For instance, what is the word I'm looking for? This is not the one that we should be worrying right now. There are other errors to be taken care of. For instance, modeling itself is I think and also converting. I'm sorry, I'm just missing that word. So basically, how to convert a strain into a measurement, that itself has far more errors than the level of accuracy that you are looking at. So for instance, here you require each of these waveforms to be reconstructed at an accuracy of 1 part in, say, 10 to the 8. So that is substantially lower than but it would be interesting to do a study like that on, say, numerical relativity waveforms to see what comes out of that. So I don't think we have, or anybody, I'm not aware of any work related to that.
Okay, thanks a lot. So let's okay, yeah, go ahead. I think this is relatively informal, right?
Absolutely.
Yeah, go ahead.
Right.
I just wanted to ask if you have a intuitive way of relating Meshfree method using radial basis to the older reduced order potential, that they also decomposing the light wave function in the basis.
Yeah.
Can the former be posited as a special case where you choose radial
Actually, good point. So the ROQ method, the way you get the basis is through a very painstaking greedy algorithm, and you require a very large number of waveforms to be injected. I mean, so the pre-computation in order to arrive at the basis and arrive at the relevant nodes is very, very high. But it has some advantages, I would grant you that. But here you can do with random placement of nodes. So it's very local. But then you can do with absolutely. For instance, you can use a low dispersion sequences, Halton sequences, or something like that, which so you throw n points and use those to basically get. So the number of points that you require are much less. The pre-computation.
Are you worried about then non-stationarity of noise keeping up?
I am worried, but I haven't done anything about it. Yeah, I don't know the answer to your question. Because I don't.
Maybe for longer sequences.
For longer sequences, yeah. That is always a problem for any of these PE methods, right? If you have a signal which lasts for months, the noise characteristics are going to change. You are going to have segments of that long duration where you won't have data. All sorts of realistic ugliness will creep up, and which you have to kind of take care of. I think that has to be plugged for all these techniques anyway. Thanks.
Yeah. No, it's informal. We'll
It's
cut
informal.
corners, so keep that in mind. That's all. So maybe that will put the pressure automatically.
Yeah,
Go ahead.
just a small question. So,
Yeah.
intuitively, I wanted to understand, let's say when we go from O4 sensitivity to O5. So, if I let's say imagine the likelihood as troughs and valleys, and I need to find the minima. So, going from O4 to O5, is the valley getting more deeper, or
No. It is that it evolves. Are you talking about why the length of the signal is much longer?
Yeah, that is also when how difficult it would be to find the let's say the minimas of let's say finding particular M chirp or these things, given the fact.
In fact, you can find it better. because you have more cycles in band. So kind of, if you do it right, then you'll be able to reconstruct these things better. But the signal gets longer, so there will be, you have to contend with that. So these are the two things. I mean, there are clever ways of not sampling the signal at the Nyquist, because it's going to spend a very long time at low frequency. So why bother at sampling at such a high rate? But yeah, I mean, if you are mindful of that, then I think you can reconstruct better.
Okay, I think that's it. So thank you very much.